Greetings. I am Dr. Suresh, Assistant Professor, PG Department of Computer Applications, St.Joseph College of Arts and Science, Autonomous, Cuddalore. In this presentation, we can discuss about link state routing. First, we will discuss what is link state routing. In link state routing, each router shares its knowledge of its neighborhood with every other router in the entire network. The following are true of link state routing. Knowledge about the neighborhood. Instead of sending its entire routing table, a router sends information about its neighborhood only. It sends to all the routers. Each router sends its information to every router on the internet network, not just to its neighbors. It does so by a process called flooding. Flooding means that a router sends its information to all of its neighbors through all of its output ports. Each neighbor sends a packet to all of its neighbors and so on. So every router that receives a packet sends copies to all of its neighbors again. Finally, every router receives a copy of the same information. Then the information is shared when there is a change. Each router sends out information about the neighbors when there is a change. The concept of link state routing. The router A sends information about the neighbors to every router. A sends the information about B, F and E to every other router in the network. Same way, B, C, D, E and F sends the information about their neighbors to all the other routers in the network. In link state routing, cost is a weighted value based on a variety of factors such as security levels, traffic and the state of the link. The cost from router A to network 14 therefore might be different from the cost from A to 23. In contrast to link state distance vector routing where the cost is invariably 1. In determining a route, the cost of hop is applied to each packet as it leaves a router and enters a network. This cost is an outbound cost, meaning that it is applied when a packet leaves the router. Two factors govern how cost is applied to packets in determining a route. Cost is applied only by routers and not by any other stations on a network. The link from one router to the next is a network and not a point-to-point cable. Then the cost is applied as a packet leaves the router than as it enters. That is outbound cost. Cost is applied when a packet leaves the router. The cost in link state routing. This is an example which we have shown here. A, B, C, D, E, F are the routers and the cloud forms are the networks number 14, 55, 92, 66, 8, 23, 78, etc. So the cost from router A to network 14 is 1. Same way, the cost from B to reach network 14 is 4. This is the outbound cost. No cost is given when a packet reaches from the network to the router. We will consider the cost only when a packet moves out from the router to the network. In a similar way, the cost is given here. We will consider link state packet now. When a router floods the network with information about its neighborhood, it is said to be advertising. The basis of this advertising is the short packet called a link state packet, which usually contains 4 fields, namely the ID of the advertiser, ID of the destination network, the cost, and the ID of the neighbor router. So this is a link state packet, shortly called as LSP. Advertiser, the router which is currently considered, the network, the cost to reach the network, and the neighbor. So getting information about the neighbors. A router gets information about neighbors by periodically sending them a short greeting packet initially. If the neighbor responds to the greeting as expected, it is assumed to be alive and functioning. If it does not, a change is assumed to have occurred and the sending router then alerts the rest of the network in its next LSP. We'll initialize the table first. Each router sends a greeting packet to neighbors to find out the state of each link. It then prepares an LSP based on the results of these greetings and floods the network with it. The following quickly shows this process for router A. The same steps are performed for every router in the network as such comes. So this is the router A, B, C, D, etc. And This is the link state packet for A. This is advertising node. A is advertising node here. This is the network ID. This is the cost, and this is the next hop. That is the next route, the neighboring router, neighbor. So A can reach the network 14 with the cost 1, and its neighbor is B. So this information is flooded to the entire network. The information is shared to the entire network. It shares the information about the neighbors to the entire network. This process is called as flooding. With the help of the link state packet, we can create a link state database. Link state database is nothing but every router receives every LSP and puts the information into a link state database. The following table shows the link state database for our sample internet. Because every router receives the same LSPs, every router builds the same database. It stores this database on its disk and uses it to calculate its routing table. If a router is added to or deleted from the system, the whole database must be shared for fast updating. This is an example of a link state database which we have discussed for the network which we have discussed earlier. Advertiser is nothing but the router A. This network, the router is connected to 14, 78 and 23. The cost to reach this network is 1, 3, 2 respectively, and its neighbors are B, F and E respectively. Same way, when B is advertiser, the network through which B is connected is 14 and 55, and the cost to reach 14 is 4 and 55 is 2, and its neighbors are A and C. Similarly, the link state database is created for all the other routers. Now we'll move to the digital shortest path to find the shortest route. First, we'll start with the local node, the router, as the root of the tree and make it the first permanent node. Then examine each neighbor of the node, and that was the last permanent node. Assign a cumulative cost to each node and make it tentative. Among the list of tentative nodes, find the node with the smallest cost and make it permanent. If a node can be reached from more than one route, then select the route with the shortest cumulative cost. Repeat steps 2 to 4 until every node becomes permanent. We'll explain now. Cost in the digital algorithm. A, this is outbound cost. When a packet moves from A, router A, and reaches the network, the cost is 1, and this is inbound cost 0. When any packet moves from the network to the router, the cost is 0. Likewise, 0 is nothing but when a packet moves from the network to the router, its cost is obviously 0. Anonymously or obviously it is 0. So the cost is mentioned here. Now we'll discuss how the algorithm works. First, consider A as a root node, and to A, keeping A as a root, 14, 78 and 23 is added. Now keep the shortest, lowest cost network as a next root node. Keeping 14 as permanent and B is added. Keep B as permanent and 55 added. Then we'll move to the next least cost network ID, that is 23. Keep 23 as permanent and E is added. And E permanent, 8 is added. So this is finished, and next we'll move to 78. Keep 78 as permanent and F is added. F as permanent and 92 is added. Now we'll move to the next least cost as 55. Keep 55 as permanent and C added, and C permanent 66 is added. Next, come to this E. Keep 8 as permanent and D add E. D is permanent, add 66, but the cost to reach the network ID 66 from D is 9, which is greater than the cost to reach network 66 through C, that is 5. So that this link is deleted. So the cost is more, this link is deleted. So here the cost is less, so you can include this link. So now 66 is permanent. 92 is permanent. In this way, the routing table is, with the help of the above information, we can construct the routing table. Each router now uses shortest path tree to construct the routing table. Each router uses the same algorithm and the same linked state database to calculate its own shortest path tree and routing table. These are different for each router. The following table shows the table developed by router A. For example, to reach the network ID 8, the cost is 4 and it has to reach through the neighbor E. See, to reach 8, A has to move through E. This is the next hop. And the cost to reach 8 is 4. The same way, to reach 55, the cost is 3 and the next route is B. Likewise, A can reach all the network through different costs through the next neighbors. This is how linked state routing works. Thank you.